RISC-V benefits and security for this specific conference. This is because like that it's very difficult to figure out why that we have, I mean like we have to study and then just actually execute RISC-V in Vietnam and then in Japan and then other places. So today I'm going to talk about background interaction and then RISC-V status and then open source security architecture on smartphone, PCs, and servers, RISC-V security trends, new direction of security, and summary. It's a whole lot of things, so I'll just actually go quick. So like in 2014, I encountered with RISC-V at Hot Chips at Stanford. And then what happened was like we were attempting to propagate SH2, Hitachi SH2 open source processor. And then so you see that here's this our flag, and then here's my dog at the time. And so what happened is like between RISC-V and then SH2, we had two booths. And then RISC-V just actually really took off. And then so we are just actually now attempting to just actually propagate this RISC-V. And then here's that RISC-V person, Yansup. And so we'll talk about this RISC-V feature. So RISC-V feature, we have like modular instruction set ranging from 32 to 6428 bits. And then you just choose necessary property, and then you come up with one instruction set. And then, so it's really a modular instruction set that covers multiple number of different parts. And also the second feature is like very dense instructions. So this is something that's comparing RV64, 64-bit instruction set with double precision floating point, single precision floating point, and then also multiplier, and then all these instructions. And then it ends up being like when you use the compiler, very close to what ARM M0 is. So it's not like that RISC-V requires more memory than ARM. In fact, it's probably less because of that, the way that the high density instruction is configured. And then another feature is, they've been talking about the Rocket chip generator, which is RISC-V SoC. And what happens is like that we had to we just actually put together a 64-bit chip with a double precision floating point and then everything, and it turns out to be very easy because, well, Rocket did everything. So, but at the same time, you have to be able to be very adept. And one designer designed that weekends, nights, and then the actual chip actual work was like maybe less than a month to just actually generate this type of chip. This is done at the University of Electrocommunication. And another thing is like all the RISC-V features are tested. Either that the chip was created or software was just actually developed before architecture release. So all the things are just actually very reliable in a sense that, and then it's very well completed. So, okay, where is like the RISC-V's application? So Semico announced that there will be 62.4 billion RISC-V cores by 2015. And Semico is a very credible semiconductor research company. And then where do they actually see the growth is RISC-V growth is like 5G base station and 5G terminals. And then this is like annually 209% of like growth is going to be expected. And then the second hotspot is like IoT, including wearables. That's actually grow at the rate of 185% a year. And then there's an in-vehicle transportation that is going to be growing at a rate of like 160% per year. So I show you like some examples. So Samsung uses SiFive's RISC-V core for 5G applications. And then Samsung uses this core for millimeter wave RF processing in 5G RF front-end modules. And then this applies to, this is going to be used in the Samsung's flagship 5G smartphones right now in mass production in 2020. And they started like the integration in 2017. And then Samsung plans to just use those core for RF calibration, AI image sensor, AI computing control, security management, and safety island for automotive. And Qualcomm has been also designing millimeter wave for some time, chip for some time. And now there's another company called NSIT EXE announced a vector processor in RISC-V, which runs at the ASIL D level. And this is called like a DR1000C chip. And then there's the first world RISC-V based processor that meets ASIL D safety requirement level for the vehicle that ISO 26262 functional safety standard requires. And another thing is NVIDIA disclosed like RC18 inference chip. This is like for AI. And it shows like that great performance per chip and then energy efficiency per chip. And then like here in Japan, like AIST, this is like a national like laboratory, is implementing TEEP on RISC-V. This is mostly software activities, but uses that PMP to implement this functionality. And then there's like a huge amount of like RISC-V server development happening very quietly. So these are the like movements that's going on amongst RISC-V. So now we're going to talk about the open source security of the RISC-V. And well, the reason why do we need to just actually worry about open source in security? Open source and security, do they mesh with one another? But really in 19th century, there's this person called Kirchhoff who just actually stated that the cryptography should still be secure even if everything but the private key is known. And this is like a driving principle of cryptography. And then in the 1970s, US government used to ban cryptographic research. That would be illegal to do it in the States. But Diffie-Whitfield thought that the privately developed Diffie-Hellman algorithm was a technology that protects individual rights. And then these two guys just actually worked together. I mean, work against them or work together with the US government. And the US government finally opened that release of like a DES specification. So like even the US government went open source in cryptography. And as far as RISC-V security is concerned, in 2013, US DARPA mandated that the RISC-V be used as a CPU for security research as funding condition. And then DARPA has been like funding the LLVM compiler for RISC-V in December 2018. So DARPA has been helping make DARPA is like a defense research arm of like the U.S. government. So, so that's where like security is. So now, essentially, that in this year's and age, what happens is like that we are separating so-called root of trust chip from like a general purpose CPU. And then essentially the reason that we are doing it is like a secure MCU, we're going to make it as simple as possible so that it cannot be broken. Whereas general purpose CPU, that has to be actually updated for performance, therefore that it's more subjective to attack. But for simple MCU, that attack is at least well known. All the methods of attack can be categorically listed, and then just countermeasures be in place. So this is how many of that chips, like Apple's like the iPhone chips, Samsung's like that chip, and BlackBerry's chip are all like configured this way. And then this is the best way to just actually reduce the attack cost. I mean, reduce the defense cost per attack cost. Anyway, so we're going to move on. And then RISC-V security status is SiFive has just announced this World Guard in October of 2019. And it is published as open source, so everybody can use. And it is reflected in implementation in Spike QEMU Rocket. And this is like very similar to ARM's like a trust zone technology. And we'll move on. So like worldwide ID, like Shield has got world ID. And then this is like that more flexible security than trust zone. And then it has got all the trust zone capabilities. I'm not going to go into too many details because there's a lot of like that presentation you can find about Shield and the World ID. Then there's this like Google started this Open Titan that's essentially like, okay, root of trust. So you have like a trust zone type of technology, and then like also in case of ARM, there's a cryptocell technology that is very similar to root of trust technology. So so we are kind of looking at the new direction of security as the high quality security technology, and there's a lot of like a counterfeit chip present and like that present. So the one on the top is the famous FTDI USB serial chip. So real chip and fake are very difficult to just determine, and but has the same function. It works mostly the same. And then there's this real and then fake analog chip down there for Maxim. So, but these are very difficult. And then like you build a board and then just they kind of come in. And then but when you take it apart, real and then fake are quite a bit different. And then price being different, but it's a good business. Therefore that the real and fake chips are always there. And also there's like so-called implant. This is like primarily to just actually extract information. And then it's got the implant chip, standard product chip, and so on and so forth. So these things actually kind of seeps in and then just somehow mingled in that supply chain. And then that has unique key frame, like in order to protect it, we have a digital way of doing this. And we do have things like we are thinking we are like one area is new ROT, root of trust, has to just detect some untrusted chips, whether they are real or not real. And then that's the next direction of like that technology we are looking at. And then now, like we do have, like sometimes we do measure the current flow of that active chip, and then using that analog chip, analog information, detect whether that active chip is like a true chip or like fake chip. And then there's like depending on how everything is, using those like type of analog information like power current, you can distinguish many more information, like whether that the chip is right or like wrong, or false or true, by using this sort of things. And then this is another area that like security, RISC-V security is starting to just actually go in. So in summary, RISC-V has made a huge progress both in technology and marketplace. And then as of RISC security, open source security technologies such as Google SiFive and closed source technology like Rambus are appearing one after another with a DARPA backend. And then we are going to move RISC-V security further. And this research has been funded by National Research and Development Agency of New Energy and Industry Development Organization, NEDO, and under that funding. So I just wanted to point that out. Thank you very much. De, これを。共有を停止して。はい。
Thank you for Mr. Kawasaki presentation. Anyone have a question?
I don't see any question, right? So maybe we could move to the next subject.
Okay.
Okay.